So what does so this is our definition, and so we have a new notion of quasi-isometry. But what does that give us here? Well, the first result it gives us is what we wanted in some sense. So there's the following proposition: the image of a quasi-geodesic of a geodesic or a quasi-geodesic. So geodesics are quasi-geodesics under a quasi-isometric embedding, a quasi-isometric embedding. So QI will be used for quasi-isometry all the time since it's such a common word. Is a quasi-geodesic. Okay. So what does this follow from? Follows from, well, what was a quasi-geodesic? It was a quasi-isometric embedding, and we are composing two quasi-isometric embeddings. Okay. So follows from the following theorem, which I'm stating as a theorem because it's foundationally important, but it's really easy. Okay. So the image, the composition of quasi-isometric embeddings is a quasi-isometric embeddings. Well, you could also take quasi-isometries. Isometries is a quasi-isometric embedding, and similarly quasi-isometry. This is really an easy result. I mean, you'll get different constants, of course. So what happens from this? So that as a quasi-geodesic is a quasi-isometric embedding, you compose it with another, you get a quasi-isometric embedding. Okay, so this I will just say exercise. Good exercise to get used to definitions. No ideas needed at all other than those common. So consequence, well, what did we start this segment with? We started with a geodesic triangle. So the image of a quasi-geodesic triangle under a quasi-isometry is a quasi-geodesic triangle. So we started with our triangle T, which was a geodesic triangle in X, and looked at its image. And the first one I pulled was saying that was thin. So, but it didn't work because it was not a geodesic triangle, but it's close. It's a quasi-geodesic triangle. Well, this doesn't seem close at all in the Euclidean context. But in the hyperbolic context, the following really remarkable result is true. Okay. It says that given constants k and c, okay, there exists m greater than 0, let's say, such that any kc quasi-geodesic is in the neighborhood Nm of alpha for a geodesic alpha. Okay, so briefly, this is a statement that says any quasi-geodesic is close to a geodesic. So proof takes work. I'm not going to say proof easy, it's deferred. So later. In another segment, we'll return to the proof. So I want to emphasize that this is one of those sort of pivotal results. This and a couple of closely related ones which give the meat to the subject of geometric group theory. You do the work in proving this result, then you can milk it to get various theorems, one of which we are seeing just now, which is that the quasi-isometry invariant of delta hyperbolicity, which is very remarkable. Okay. But now, right now, what I'll do is just show you why this is very false in Euclidean space. So the key point here is M depends only on K and C. Okay. So let me take Euclidean counter examples. So how does a quasi-geodesic look? Even with constant 0, a Euclidean counter example would be a semicircle or any chord which is less than a half circle. Okay, here it is. So this is of course the geodesic, and this top half, which we already saw, this is a pi by 2, 0 quasi-geodesic. Okay, so this has become the diameter, so the length of the geodesic, and any chord here will be even better in terms of the ratio of distortion. So Euclidean counter examples. Okay, and so suppose this distance here is r, then the distance between this quasi-geodesic and this geodesic is also r. Okay, so we can get, so no M works for pi by 2, 0. In fact, any k greater than 1, any k greater than 1 and c equals 0 or c positive. So in basically no case in the Euclidean space do you have this result. You can just take chords instead of taking arcs to see counter examples. And an infinite example is the following, that I start off with a curve and then I spiral out. Well, what happens if I spiral out? So this is not bounded distance from any geodesic. I assume this is from any geodesic. Okay. In the first case, what we saw is, of course, because it's a finite quasi-geodesic, it is bounded distance from a geodesic, it's bounded distance from a point, but not in a uniform way, depending on the constants of distortion. This case, if you take an infinite spiral, it's a quasi-geodesic, but it's not. You have to set it up a little carefully because there are quite significant shortcuts here. You have to spiral out fast enough to make it a quasi-geodesic, but you can do so. It's not bounded distance from any geodesic at all.